Hey, what's going on, guys? MCTS here. The very last method left here to implement is the backpropagation. So that is very simple. We just simply need to update the visit count and the scores in every single node from the leaf node where we currently are and up to the root node. So without further ado, let's actually go for it. So here I want to say update nodes, visit count and score up to root node. So I can simply say while node is not none, and the condition node is none would be as soon as we reach the root node, because it doesn't have any parent node. So here we actually need to do the following steps. So first, update, let's say update nodes up to root node. Okay, and here we want to update node visits. So I can simply say node.visits plus equal 1. Then we want to update node score, nodes visits, node score, and here node.score plus equal the score. Okay, and finally we want set node to parent. So node equals node.parent. So here's the simple trick. As soon as we set, well, let's say we have a node. So we just update its stats here, and then this node would be equal to node.parent. So this node would already be kind of would be equal to the node which is one level up compared to this node. So this is the child node, and after this line executed, it starts being a parent node. And then in the parent node, again, we're updating the visits and the score, and then going one level up again, and again updating the stuff, one level up, and we're repeating this until there is no more one level up available. So while node is not none. So while node is none, that means that we reach the root node. So that's kind of pretty simple idea behind this backpropagation. So maybe it's a bit tricky word and might seem like something complicated, but on the real deal, this is quite pretty simple. Okay, guys, so this is it regarding the Monte Carlo tree search algorithm, believe it or not. So let me just quickly check up if everything is working. Oh, hold on a sec. Here we need to say self.getBestMove, because we're referencing the method of the Monte Carlo tree search. Otherwise, it would have given an error. Okay, and just to make sure that we don't have any print statements. Okay, so we don't need this one as well. Okay, now this should be kind of fine. So the very first test I would like to take here would be to make our tic-tac-toe engine, if we can call it like that, plane versus itself. So I just want to open the terminal in the current working directory, and by typing python 3 tic-tac-toe.py. Okay, it gives, well, what is this? Oh, this is from the, okay, this is from the previous this is from the previous output. So here let's say loop to play let's say AI versus AI. So I simply say like while true, quite pretty trivial, while true. And here first I want to, yeah, so best move would be equal to board, oh sorry, what am I doing, Monte Carlo tree search dot search, and initial board as an argument here. Okay, yeah, nothing much, right? So find the best move, and then make the best move on board, so literally updating the board. So board would be equal to best move, and assuming this is the tree node, we need to reference dot board, so to get the actual position that is associated with that node. And let's print board, so print board, and the very last thing would be to to have this user interrupt here, so just input. I will delete this code when we test it, so no need to provide too many commentaries. So let's try the stuff again, and now it's kind of searching already. Okay, so a strange solution for the best move, for the best first move, but anyway, let's have a look. Okay. Okay, and AI seems to be winning versus itself. Okay, so let's make a little error handler here, but obviously don't really need that much, but okay, yeah, I'm a bit confused by the results because the version, yeah, I've been watching this version basically, so this one would end up with a draw, and obviously which is what is true for Monte Carlo research, is that we need to make sure that there are enough of iterations within the search to make it play the strongest game possible. And again, like the more iterations, the more the stronger play we will have, because anyway we have this random rollout here, which is here's the random rollout that actually gives some sort of randomness to the game and to the results. Well, anyway, just want to run this several times to yeah, most likely it would be choosing this move. Yeah, so most likely it would be playing a draw, but as you've already seen, it also it's not kind of perfect because it's not that enough iterations to actually make it perfect. But if we make if we say here like 10,000 instead of 1,000 iterations, it would be taking kind of too long, and we don't really want that. And again, like the so-called vanilla Monte Carlo research algorithm is not that strong as alpha beta, because I mean as minimax, because it's not a brute force, and the entire idea behind this is that it is not a brute force, it's kind of selective search, so just trying to find what considered to be the most promising moves. And this is just an example of the reinforcement learning and how it works in its vanilla form. Well, anyway, as far as the concept of the fact that the search is working has been just proved, we can now enable our board loop, and within our board loop here, where we already made this placeholder, so make AI move. So here I just want to say so what was I doing here? Okay, so best, so let's say search for the best move, so best move would be equal okay, hold on a sec, I didn't create a Monte Carlo research instance, I believe. So here I want to create Monte Carlo research instance. Okay, Monte Carlo research like this. Okay, so here I want to say Monte Carlo research dot search, and this self is the current board position that we have. And now to make the move, we need to say self equals best move dot board, and in theory this should result in a plain game of tic-tac-toe. So without further ado, let's actually try to test it. Okay, so it asks me to make a move, so let's say 1-1, Okay, so it's probably the strongest response possible here. Okay, so I will now try to win. So I would place 3-3. And if it didn't place it here, but say if it did place it here, I could have played cross here, and then if it just blocks here or here, then I can win. But this already is a drawn position. So now for me, in order to avoid losing, well, actually, first let's check that the AI is actually capable of winning. So let's try some dumb move like 1-2, say. Okay, and AI wins, which is good. So the first test is just fine. Now let's try some other stuff. So I need to say 1, 2, 3, and 2. Oh, I just probably place somewhere wrong place. Okay, sorry guys. So let's try again. Okay. Even though it plays the same move every time, it doesn't mean that it would obviously play in this same move every time. So it might be some variety, because you remember, like, there might be return one or the random of the best moves available. So it doesn't obviously mean that it would always be playing the same game. So 2 and 3, I guess this is the right. Okay, so I've prevented him from winning here, and now I need to say 1. So x is 1, and nope, x is 3, and column is 3, and row is 1. Okay, and now the only move left would be 1 and 2. Excuse me. Oh, it's just made something horribly wrong. It's illegal command. Whoa, illegal command. Hold on a sec. This is interesting. What's going on here? Now he says this is the illegal move. I don't understand something here, probably. Okay. This is a little bit strange, so let me see. Well, for now I just wanted to try accept this part. Just to print what the exception is. So print and E. Okay. Okay, 2, 3. Okay. 3, 1. Okay. 1, 2. Game is drawn. Okay, now I don't know what did I do wrong previously. Oh yeah, I see what was wrong there. So after my move, after user's move, it was already a drawn state. So that's the idea. So that's the reason. Yeah, we really need to try accept the AI move. So actually, if the game, after the user's game we reach the terminal state, either drawn or won state, that means that AI would be trying to search the best move for the position where no more legal moves are available. Yeah, so I think this simple try accept should make the entire trick. So here, let's say so legal moves available, and here this is actually the game over. Okay, and we really shouldn't see this error, so I just pass here. Okay, let's try some different. So let's say 3, 3. Okay. Yeah, I just thought I would be playing here. Okay, so this is also nice. And probably, hold on a sec guys, just another little trick. So probably I would like to print the board also after human is making a move. I think this should be fine. Well, actually, I meant 3, 1. Okay. So yeah, now it's much better. So here I made a move, and the AI moves right over in here. Well, it's a little bit strange to me. So let's say 1, 3. Okay, am I gonna win this game? It seems like I'm gonna win this game now. 2, 1. Okay, I won the game. Well, this is a little bit strange, so let's try again. You're always gonna be playing. Oh, okay, so that was just one of the exceptions that I was talking about. So due to the random rollouts and the nature of Monte Carlo research algorithm itself, computer actually did allow me to win. So this shouldn't happen anymore. So now I say 1, 3. Yeah, and now it's gonna be a draw. So 3, 2. Now 1, 1, and 2, 3, and this is a draw. Well, okay, guys. So this is it from my side. I hope you've enjoyed the entire tutorial series on this tic-tac-toe and the Monte Carlo research algorithm in cooperation. The next steps regarding this project and regarding my thoughts in general in kind of machine learning and neural networks is actually to, well, you probably know that there is a modern project by Google's DeepMind, which is called, first it was AlphaGo, then it called AlphaGo Zero, and eventually the project name is AlphaZero, and now they've created even the updated version. So that is the general algorithm that combines Monte Carlo research and the neural networks in order to master whatever game without any human knowledge in the particular game domain. And they, using this algorithm, they managed to beat world chess champion in Go, in chess as well. Well, it's not that big deal basically in chess. In chess they managed to beat Stockfish back in those days. But well, obviously it's arguable regarding the hardware being involved in the match, but that's not the point at the moment. So anyway, the downside of this Monte Carlo research algorithm is this. Well, basically, yeah. By the way, regarding the rollouts, in one of the previous videos, I said like this random rollout is the essence of the Monte Carlo research. Well, it's not exactly true because we obviously can have not only this random rollouts, which are also known as the light rollouts, but we can also have some additional logic to make moves not randomly but somewhat different. In that case, it would be kind of known as the heavy rollout. But anyway, we can go even further, and instead of making a rollout, we can use a neural net to predict the value for the current board position. And again, like at the moment, I'm working out some different opportunities on how exactly to use these neural nets. And again, like there are two options that we can make use of in regards to Monte Carlo research algorithm and neural nets. So the first idea is the move ordering or move selection. So if we just slightly alter our UCD formula, we also can take into account the predictions of the best move from the neural net if we implement that neural net and we have those predictions. On the other hand, we can use values that are predicted by the neural net. So this might be either another neural net. So we can have two neural nets like in the old implementations of AlphaGo by Google DeepMind. They had two neural networks, one for predicting predicting the probability of making the move, and another network to predict the game result. So that's the idea. While in the latest AlphaZero version, they've embedded these two ideas into a single neural network that actually outputs both the probabilities for every move available, so how likely it's about to be done on the board, and on the other hand, what kind of winning probability of that move is. And then they are using the Monte Carlo research to generate the training data to update the neural net every not every iteration, but every 1600 iterations. I'm not sure, don't remember really, don't remember exactly. Well, anyway, that sort of an approach is really cool, but for me personally it's a little bit too tricky to master. And even though I understand that in general after reading all those papers by DeepMind, but still it's a little bit of a rocket science to me at the moment. So I will try to come up with some sort of a simpler approach, but with the same ideas. So just to give you an idea where exactly we can make use of the neural nets in cooperation with our Monte Carlo research algorithm. So we can use the neural net to influence the decision on which particular move to pick up within our UCD formula here. So while we're selecting the mode, and on the other hand, we can use the neural network to predict. So the first is the classification neural network. The second would be the regression neural network. So just to predict how likely this current given site is about to win, assuming the particular bird position. Well, anyway, really lots of job needs to be done for me personally to get done with that. And again, like bearing in mind that my ultimate goal is actually to apply that to chess one day and to make first Python tutorial on neural net chess engine, and then most likely I would be happy to implement that in C programming language because that just would be faster. But if that ever about to appear, that would obviously be on my chess programming channel, and you can see the link to the description on the top right corner of your screen now. Okay guys, so this is it from my side. I hope you've enjoyed this tutorial series. I hope to get back to you as soon as I find the way to embed, to create and to embed neural networks to this, along with this Monte Carlo research algorithm. So this tutorial hopefully is not yet over, and I really hope to continue it as soon as I work this stuff out. So see you next time. Until then, and take care.